Hello, Physics 2. Okay, so welcome to part 1 of Monday's lecture. So last time we were starting to derive the equations that joined the electric field and the magnetic fields. And we got some interesting relationships so far. So we looked at how electric flux d phi dt is equal to EVH, and we were able to also determine that B is equal to mu naught epsilon naught E. So I'm kind of skipping ahead from where we started last time. So, and I warned you, got you super excited that we're about to see something very, very cool. So, all right. We've got a couple of different relationships. I mean, The Bachelor has nothing on this. I think that makes me relevant. All right, so let's put it all together. All right, so let's look at the speed of propagation. We also had E is equal to VB. So, speed of propagation. E is equal to VB, and B is equal to mu naught epsilon naught VE. Yeah? Okay, so we've got a V here, and we've got a V here. Let's solve for it. Okay, so electric field is equal to V mu naught epsilon naught VE. So all we have done is we've just plugged that into there and we've rewritten it. Okay, cool. So then let's see, we want to get V by itself. We've got two V's here, so we're going to end up with a V squared. So we've got E over mu naught epsilon naught E is equal to V squared. Okay, interesting. V squared is equal to 1 over mu naught epsilon naught. Okay. Interesting. Let's keep going. So V squared 1 over mu naught epsilon naught. V is equal to the square root 1 over mu naught epsilon naught is equal to the square root 1 over 4 pi epsilon naught times 4 pi mu naught. So, and all I've done there is just so that we can plug in our normal constants, okay? So V is equal to the square root of 9 times 10 to the 9 Newton meters squared over Coulomb squared, and 1 times 10 to the 7 amps per Tesla meters. Okay. Plug that into your calculator. V is equal to 3 times 10 to the 8 meters per second, the speed of light. That's why we kept mu naught and epsilon naught. We get the speed of light from these fundamental constants that they discovered before we knew about the speed of light. We'd been suspecting the speed of light for a while, but this is it, guys. This is why you call something a fundamental constant. This is what it means. These are the implications. We've got about 7 of them. Mu naught, epsilon naught, speed of light, C are 3 of them. And they are related. And I hope your minds are blown right now. Because if not, check your pulse. It is that exciting. All right. And on my next page of notes, bam, we got there. It took us a year, but we got there. All right, so let's keep going. Now that we're all super psyched and ready to go, Maxwell went through these calculations. So we had an idea. We had an idea. People have been trying to measure speed of light for a while. But the idea of it being a constant came from Einstein. Light was around 3 times 10 to the 8 meters per second. We knew this before we really understood the properties of light. And so basically this laid the groundwork for Einstein. If I could spell seen correctly. I quit for Einstein to come and pull these ideas together. Light is electromagnetic radiation. Light is electromagnetic radiation. It is a packet of pure energy with a particle nature, a wave nature, a quantized nature. It is so much cooler than your wildest dreams could ever imagine. And I'm not exaggerating this. The more you study it, the more you realize you don't understand it, and it is pure magic. From a scientific perspective, of course. Okay. Just calm down now. All right. So, now that we know light, now that we can start to understand light, properly, let's play. So we need to understand it now from this field perspective that we have been building all semester. I tell you, this semester is a crescendo. We are at fortissimo. All right, so let's look at the relation of the electric field to the magnetic field in an electromagnetic wave. So EM stands for electromagnetism. So sometimes I'll talk about taking E and M. That's just electromagnetism. You take a whole class on it if you're a physics major. And so there's 2 main undergraduate courses where you really get to study light. Well, 3. So electromagnetism is one of them. Fundamentals of optics, it's not offered everywhere. It is offered here. You get to study light, and then quantum mechanics. You get to study a little bit of light properties in that class as well. So, all right, so moving on. So E is equal to CB. We can now update the velocity to the speed of light. And so also the velocity of the pulse is in the same direction as E cross B. So you take the cross product of E cross B and you'll get the speed of V. So light and its ilk, which is a word we do not use enough, our electromagnetic radiation. And when you're thinking about it, E fields are perpendicular to B fields, both of which are perpendicular to the velocity. So if we draw this out, here's our E, here's our B coming out of the page, and I've just drawn you a photon. This is light. This is a pulse. Okay, so next up, we need to move on to light waves. Or sinusoidal radiation. Okay, so let's do it. Maybe I can turn the page. Accelerated charges and radiation. All right, so we know E and M waves travel at the speed of light. So we know that. So how do we produce electromagnetic radiation? You know, these traveling electric and magnetic fields. We accelerate a charge. Beautiful, isn't it? Oh, gosh. Love this. So you've got your charge here. You've got your electric field. Radiating in all directions. So at rest, let's say we've got two observers. Here's observer 1 and observer 2. So it's just going to take time t for this electromagnetic radiation to be measured. And for this electric field, we don't have electromagnetic radiation yet. We just have an electric field because this charge is at rest. And so you can just remember electric fields travel at the speed of light. So whatever distance you are away from it, that you can easily find the time it will take by using the speed of light. All right, so now we're going to accelerate the charge. So we're going to push the charge up and to the left. So let me write in observer 1, observer 2. Here's our Q. And now what you're going to get is you're going to see within this electromagnetic radiation is you're going to get this little pulse, which is the change of field. And it does not travel there instantaneously. So In this case, once the pulse gets to observer 1, which I meant to draw observer 1 here, awesome, the observer notes the change in field. And observer 2 sees it as it was. So you don't always get to, if the pulse has not traveled to you yet, you don't get to see it. By the way, what we're building towards, and I'm going to hint at this now, this is how we see starlight. You are looking into the past. You are waiting for those propagations to reach you. This is how we see the universe. All right, so I'll write some things out. So fields move through time and space. So, and it will need to reach observer 2. So now let's think about, from a theoretical perspective perhaps, how long it will take for observer 2 to see this change in field. The distance between observer 2 and the original location is R is equal to CT. The time observer 2 will see the updated electric field is T is equal to V over C. So this looks like pulses we've analyzed earlier. So essentially, we're looking for when this reaches observer 2. That's the pulse right there. By the way, you don't need to write everything that I write down. I've just been writing down more with this online format just to make sure that hopefully things aren't being lost in translation. Because in class, I can check to make sure that you're following with me. I can say more and write a little bit less, and well, I can ask, but if someone answers me, I'm going to be really freaked out. Okay, so our accelerated charge is producing EM radiation. Okay, so but we know how to handle this. So by using Faraday and Ampere-Maxwell, and that moving bit of radiation must have a magnetic and electric field traveling through empty space. E cross B is the direction of propagation. And if you accelerate a charge and bring it to rest, there will be two pulses. One to accelerate, one to decelerate. Okay, so let's take a closer look at this field now that we've kind of summarized these ideas together. So you start to get something that looks like this. Where this is the propagation. Oops. And then you have E transverse, the field from acceleration. And so that's basically the idea of it, and then now visualize it in 3D. So there's an excellent picture in your book of this three-dimensional field. Because they have computer programs to draw these, I am not even going to remotely attempt to replicate it because it will look terrible. But I recommend looking at it. It'll give you a more complete picture of how to think about these types of fields related to the propagation of accelerated charges. So, way cool. Okay, so the field will radiate out. So this transverse E field is proportional to Q A perpendicular. A perpendicular is projected acceleration. And so we can write the radiative, or what I'll more commonly write as E-rad, because it's, radical. Oh, you students who have no idea about how tubular 90s vocabulary was. All right, so 1/4 pi epsilon naught minus Q A perpendicular over C squared R. And the direction of E transverse is minus Q A perpendicular. And there is a 1/r relationship, which is different to the usual 1/r² relationship. And this allows us to see stars. Stars that are millions and billions of light years away. Just imagine if it diminished at a 1/r² relationship, we could never see them. So we often think about just the magnificence of our designed universe. And sometimes we think about it purely from an analytical perspective, but I want you to take a moment to draw in the beauty we get to realize because of this relationship. This lets us see space. We get to see the universe we live in. That is incredible. Take a moment, take that in. All right, so this actually has a relationship which allows atoms to be stable. It's these properties which give the stability of atoms. So, classically, any accelerated charge emits electromagnetic radiation. And electromagnetic radiation accelerates other charges. Therefore, a flow of energy is associated. And remember, we can't get something for nothing. Classically, this implies accelerated charges lose mechanical energy by emitting radiation. And classically, this is a problem for atom stability because, well, think about how electrons move around the nucleus. They're orbiting. So we have accelerated motion. So the electron should, classically, lose energy. From radiation. The implication of that, of course, would be this. Destruction. No more atom. And this would happen in t equal to a fraction of a second. The whole universe demolished. Enter quantum mechanics. Quantum mechanics solved this dilemma. With discrete energy. E must keep true to the energy level. There is no mechanism for losing energy. So what you have, here's our nucleus, let's say, here's ground, here's our electron. It can emit a photon of light of a very specific amount of energy, but it's one photon. It is not continuously radiating photons. It keeps its energy. It does not lose it. And thus, the principle of the conservation of energy is not violated. This is the beauty of modern physics. Solving classical problems and building on the knowledge that so many men and women have put together for centuries. All right, I'll stop part 1 right here, and I'll see you next time for part 2.